Well, it's my pleasure to give the first presentation in the morning. I usually don't get up this early, so. So today what I'm going to be talking about is some of the recent results that came from NASA's gravity mapping mission that went to the moon called GRAIL. The acronym GRAIL should sound familiar if you're not a planetary scientist. It's a mission that's very, very similar to the mission GRACE. GRACE is a two-satellite mission in orbit around the Earth whose objective is to measure time variations in the gravity field of the Earth, such as variations in mass associated with the ice caps and mostly hydrodynamics. But the objective of GRAIL is to not measure time variations in the lunar gravity field, but rather to measure the static gravity field to high precision. So this mission, for this talk, I have to, before starting, I have to, of course, to acknowledge Maria Zuber, who is the principal investigator of this mission. If it wasn't for her, we wouldn't have any of these superb data to talk about today. Okay, so with the moon is a really great place for studying planetary science. It turns out we have a large number of data sets. Unfortunately, most of these data sets we have only tell us about the surface of the moon. For example, just recently we have some global spectral mapping from the moon, most recently from the Chandrayaan-1 M³ instrument. During the 1998, a lunar prospector went to the moon and made the first global maps of the composition of the lunar surface, outlining this really weird geochemical province on the near side of the moon. Today we have the Lunar Reconnaissance Orbiter, which is still in orbit around the moon, making global images of the surface. And also, as a result of the Apollo missions, and also the Russian Luna missions, but also the lunar meteorites, we have a large number of samples to work with. We have, in fact, over about 400 kilograms of samples. Now, the problem is that if you're a geophysicist, you might not care about these data sets, because we're really interested in what's going on below the surface. And in order to study the interior structure of the moon, what we really need are geophysical data sets. And that was what the objective of the GRAIL mission was to give us some better information about what's going on below the surface. Okay, so in this talk, it's going to be divided into roughly three parts. First, I just want to give a brief overview of what the GRAIL mission is, in case you haven't seen it before, and then give some just a brief summary of the initial results that were published just after the primary mission. And then I'll talk about two specific questions in a little bit more detail, both concerning impact craters. First, I'll show that GRAIL can actually detect buried and ancient impact craters, which gives us a better understanding of the impact environment in the near-Earth system. And secondly, I'll try to show that as a result of some of the largest impact basins, that these impact events may have actually excavated through the entire crust and into the mantle, allowing us to probe the composition of the lunar mantle. Okay, so let's start with the gravity field of the moon. This is one of the best gravity maps we had before the GRAIL mission, which came from the analysis of radio tracking data from the Lunar Prospector spacecraft. And the only thing I really want to say here is that well, first of all, the right side of this image here corresponds to the near side, and the left side corresponds to the far side. And the way that this map was constructed is that you send a radio signal from the spacecraft to the Earth, and then you measure the time of flight of the radio signal and the Doppler shift in order to reconstruct the orbit. And then from reconstructing the orbit, you can reconstruct the gravitational forces that are acting on the satellite. Now, because the moon is in synchronous rotation, every time the satellite goes behind the moon, you can't communicate with the Earth. So because of this, there's a huge difference in quality of the data for the near side, which is directly visible from Earth, and the far side, which is not visible at all. So this was a primary objective of the GRAIL mission, which was to make a global gravitational map of the moon and fill in this hole of data on the far side. Okay, so the mission, start the animation. So this mission here was a Discovery class proposal, which was selected in 2007. In essence, what NASA did is they gave the PI about $450 million with the constraint that they had to launch something in a 3-year time period. The launch was on September 10th in 2011. We took this weird trajectory to get to the moon, which took about 3 months. And then we inserted the two spacecraft into orbit around the moon on December 31st and January 1st, respectively. And then we used a 3-month time period to circularize the orbit, and then we had a 3-month primary mission. And this is just showing a quick animation for what the measurement principle is. So here we see the two satellites being circularized. We put the satellites into an orbit around the moon where the altitude is roughly about 50 kilometers above the surface, and the distance between these two spacecraft is roughly about 200 kilometers. And then what we do is we measure the distance between these two spacecraft with a precision on the order of a micron. And by using these time variations in the distance between these two spacecraft, we can in fact make a map of the gravitational forces that are acting on them. So this is just showing the way that the measurement techniques works. The spacecraft are kind of in a stationary orbit, and the moon rotates underneath it, allowing us to make a global map. And here it's just showing that if you have more mass on the surface, such as due to a mountain, it's going to affect the way that affect the orbit of these two spacecraft, giving rise to differences in distance between the two. Okay, so this is a map of the gravity field before the GRAIL mission. You can see there's pretty much this big noise blob on the far side of the moon in the center of this image here. And after only a couple months of data from the primary mission, we pretty much filled in this hole and made a gravitational map of the moon, which was orders of magnitude more precise than what we had before. Now this data set here comes only from the primary mission when we were mapping from an altitude of 50 kilometers above the surface. But in fact, we actually did better than this. After the 3-month primary mission, NASA allowed us to have a 3-month extended mission. And what we did is we lowered the altitude of the two spacecraft by a factor of 2 to roughly about 25 kilometers above the surface on average. Now, because the two spacecraft were in eccentric orbits, we actually got closer to the surface than this average 25-kilometer altitude. And this map here is showing the minimum altitude of the spacecraft as a function of position on the surface. And what you can see here is that these greenish colors correspond to roughly about 20 kilometers altitude, and these blue colors here correspond to less than 10 kilometers altitude. And since the spatial resolution of the gravity field that we measure depends on how close we are to the surface, what this shows is that in these regions that are blue, we actually can make a gravitational map that has a spatial resolution of a few kilometers. Okay, so let's go through some of the initial results. Here I'm just showing, we'll start with the near side of the moon, which is the hemisphere that we can see from the Earth. On the left here I'm showing topography, and on the right I'm showing the free air gravity from GRAIL. Just a few things to point out. First of all is that the gravity in general is well correlated with the topography of the moon. And this should not be too surprising, because if you have, for example, a mountain here that's a couple kilometers high, there's extra mass on the surface, and that gives rise to a positive gravitational acceleration. If you have a hole on the surface, there's less mass, such as in the center of this crater here, and that gives rise to a negative gravitational anomaly. Now, the one thing that's curious is that there is one big exception to this rule, and these are the biggest impact craters on the moon. So for example, if we look at this crater here, Imbrium, Serenitatis, or Crisium, we see that these impact craters are associated with these huge positive gravitational anomalies, even though the topography is negative in the interior of these craters. This has been known since the Apollo era, and these craters are called mass cons because there must be some kind of mass concentration below the surface to account for these gravitational anomalies. And I'll talk about this a bit later in my talk, but the general idea is that during the impact event, these craters excavated the crust and the mantle rebounded up to the surface. And since the mantle has a higher density than that of the crust, that accounts for a part of this gravitational signature that we're seeing. Okay, so let's go to the far side of the moon. The far side of the moon is very different than the near side. This has been known for a long time. Almost every single data set we have for the moon, whether it's geochemistry or geophysics or samples, suggests that there's this dichotomy between the near side and the far side. And this is reflected in the geophysical data as well. As you can see here on the near side, we have these huge impact craters with these huge gravitational mass cons. But when you look at the far side of the moon, you see fewer of these big mass con signatures. One thing you can see is that there's this huge giant impact basin here, the South Lacan Basin. This is the largest impact structure in the solar system. It does not have a corresponding gravitational signature, and the most likely explanation for this is that this crater formed very, very early in lunar history, perhaps about 4.4 billion years ago. And this was when the crust of the moon was hot, so that this crater here was isostatically compensated, giving rise to a very muted gravitational signature. But in terms of other impact craters, most of the big impact basins on the far side of the moon are much smaller than on the near side. And on top of that, the signature, the mass cons that are associated with them are much smaller. So just taking an example, Serenitatis, which is a typical mass con basin on the near side. And then if you look at one of the biggest impact basins on the far side here, Moscoviense, you can see there is a mass con there, but it's very small compared to those that we see on the near side. Okay, so one of the first things that the GRAIL team did was we tried to estimate the density, the bulk density of the lunar crust. And this is very easy to do because at the wavelengths that we're interested in, there's very little lithospheric flexure occurring on the surface, and the gravitational signature that we're seeing is mostly due to a reflection of the surface topography. And since we know the topography, we can invert for the density of the crust. There's a few things I should point out here. First of all, this is the near side, this is the far side, and these white regions here are the regions we didn't analyze because these are the Mare basalts, which complicate our analysis. But the first thing I should point out is just the average value of the density that we inverted. The average value we find is about 2,516 kilograms per cubic meter. Now, this number probably doesn't mean anything to you, but it turns out that the density of the mineral grains in the samples that we have from the moon, and also based on remote sensing data, suggests that the grain density of the lunar crust is about 2,900. And this is a number that all geophysicists have used since the 1970s. So the number for GRAIL is suggesting that the crust of the moon is considerably less dense than all the previous studies have suggested. Secondly, what this map shows is that there's some important spatial variations in bulk density of the crust. And these variations in bulk density are mostly correlated with impact craters. So for one example, this is that giant South Palaecan basin on the far side. It has a generally higher density than the surrounding crust, and this is because it's been known for a long time that this region of the moon has a atypical composition that is rich in iron-rich minerals. Also, we can see that the density appears to be correlated with smaller impact craters as well, where the exterior of many of these basins is negative. It's much smaller than typical. Okay, so what we can do next is using some a priori information about what the grain density of the crust is, that is the density of the minerals that make up the surface, we can make an estimate for what the porosity of the crust is. Our interpretation is that the difference between the grain density and the bulk density that GRAIL measures is just due to porosity and void space in the crust. I should also mention that it's a complicated part of this talk, but the porosities that or the densities and porosities that we're measuring here should be considered reflective of the upper several kilometers of the surface. So it's reflective of at least the range of topography on the surface, which is several kilometers. And we have a recent study that just was published in GRL suggesting that this porosity actually extends to perhaps 10 kilometers depth as well. Okay, so the first thing is the average value of the porosity that we invert for the surface is about 13 or 14%, which is a lot. I think the porosity for just for spear packing is about 33%. So this suggests that the upper portion of the lunar crust has just been fractured a lot, and that there's lots of void space. And our interpretation is that this void space and fracturing is a result of the impact process. And this is because the moon is very geologically inactive, and it's been subjected to meteoroid impacts over 4.5 billion years, with some of these impacts being enormous, like the South Palaecan Basin, but other impacts occur on a daily basis, which are smaller, that have only meter-sized scale sizes. On top of this average value for porosity, we see that there are lateral variations in porosity, and these again are correlated with impact basins. In general, in the interior portion of the basins, the porosity is lower. This is to be expected because when the basin forms, the central portion of the basin is hot, perhaps partially molten, and that portion of the crust should crystallize with zero porosity. And then outside of these impact basins, we see in general that there are enhanced regions of porosity, and this is not too surprising as well because the ejecta that comes out of these basins is going to be highly fractured, and also the passage of the shock wave through the crust is expected to fracture the surrounding crust. Okay, so next thing that we did is that using our knowledge of what the bulk density of the crust is, we made a map of the Bouguer anomaly. In essence, what we do for this map is we take the free air gravity and then remove the contribution of the gravity that comes from the surface topography. And everything that we see here that remains is due to some kind of gravitational anomaly that's occurring from something below the surface of the moon. Either this could be volcanic intrusions in the crust, or it could be variations in thickness of the crust. So the first thing we did is we made the assumption is that most of these Bouguer anomalies that we see are the result of variations in crustal thickness. And we made a crustal thickness map from these data here. And what this shows, again, shouldn't be too surprising, is that the crust turns out to be very thin in the interior portions of these large impact basins, such as Imbrium and Serenitatis here. The crust is only about 10 kilometers thick, whereas the average thickness of the crust, at least in this model, is about 30 to 40 kilometers. But what is surprising for me, and I'll talk about a little bit later in this talk, is that there are several impact basins where the crust is predicted to be almost absent. For example, the basins Oriental, Crisium, Humboldtianum, Moscoviennes, Apollo, and Poincaré, the thickness of the crust in their interior is predicted to be less than 5 kilometers. And in fact, there are two impact basins, Crisium and Moscoviennes, where our model predicts the crust to be exactly 0. So this suggests that perhaps at least these two impact basins, and perhaps others, might have excavated through the entire crust of the moon into the mantle and may have exposed mantle materials on the surface. Okay, so the next thing we did is we started to look at some of the fine scale structure that was in the Bouguer anomaly map. As I mentioned before, the Bouguer anomaly map is derived after you remove the gravitational attraction from the surface topography, and you're left with a map that is fairly smooth. You only see these large scale structures associated with mass cons. But it turns out that you can actually do better. What we did is we started playing around with gravity gradients, which is just the derivative of this map, and that highlights some of the fine scale features that are not easily visible to the naked eye in an image like that. And what we see is there's actually a lot of fine scale structure in the Bouguer anomaly map. And in fact, we found that there appears to be a large number of linear gravity anomalies on the surface of the moon. And one of the most prominent ones here is just as one example. This is a linear anomaly in the Bouguer gravity gradients. It has a length of several hundred kilometers. It's extremely straight. And our interpretation of this, which may be incorrect, but the easiest interpretation is that this is a result of a magmatic dike below the surface. This is just one example from, I believe this is Shiprock in the US. And based on our modeling of the size of this dike, even though most dikes that we see when we go out and to outcrops on the Earth, they're very small, only about 1 meter in diameter. It turns out that this dike here is predicted to have a diameter that's about 10 kilometers, which is pretty extensive. And another thing that's curious is that actually when we look at the geochemical data from the surface, we don't see any signature of this. So this suggests that this dike it was deep below the surface, and it has not been, the volcanic materials have not been excavated to the surface. Okay, so now I'm going to talk about one thing, two different topics in a little bit more detail. And the first one concerns impact basins, because this is the primary signature that GRAIL sees in the gravity data. And the first thing is that using the GRAIL data, we can make a better inventory of the number of impact basins that exist on the surface of the moon. You might think that it's easy to count impact craters on the moon. It is, but the thing is that since the impact cratering is one of the primary geological processes, it's also the primary erosional process. And older craters get buried by younger craters. So just by looking at geomorphic maps of the surface from images or from chemical data, it's not always obvious that we see all the craters that formed on the moon, because some of them may have been buried in the past. So this is just one example here. This is a crater. This is topography on the left and the Bouguer anomaly on the right. Here's a crater Lorentz, which is a couple hundred kilometers in diameter. This has been known for a long time to be a prominent impact basin. And when you look in the GRAIL gravity data, lo and behold, you see a mass-con signature in its interior, which is a result of this basin thinning the crust and uplifting the mantle towards the surface. Now, what may not be obvious to everyone, perhaps if you're a geologist, you can see this, but there's here, at least in the GRAIL gravity data, you see there's another mass-con signature just next to this basin, which has exactly the same size as Lorentz. But when you look into topography data or other types of imagery data, you really don't see anything. So this suggests that this here is a giant impact basin which was buried by weathering because it formed close to this Lorentz basin. So in essence, the Lorentz basin here just excavated a lot of material and placed a few kilometers of ejecta on top of this basin. So it's not visible in the surface topography and the other surface data sets we have, but it is visible in the gravity data. Okay, here's another example from the near side of the moon. This is, again, it's a topography. This is just showing that there's a prominent impact basin, Nectaris, on the near side of the moon, which has this huge gravitational anomaly in its center. When you look at the gravity map, you see other signatures here, and our interpretation is that this huge gravity anomaly, just next to Nectaris, is an ancient degraded impact basin. Again, if you look into topography or other data sets, you don't really see anything because this basin is older than Nectaris and has been affected by the Nectaris impact ejecta that covered this basin afterwards. Okay, so using these types of data, we came up with a global inventory of lunar impact basins, which are circled on this map here. I'm only showing the biggest impact basins for clarity. And the one thing that struck us is that there appear to be more big impact craters on the near side of the moon than the far side. In particular, first of all, let's just ignore the South Polacan Basin. This is the biggest basin in the solar system, the oldest basin, and everyone knows it's very, very atypical. So just ignore this basin for now. But if we just use a cutoff diameter of 320 kilometers, we find that there are 8 large impact basins on the near side of the moon. And with the same criteria, we find that there's only one of these impact basins on the far side, which is this Oriental basin, and Oriental actually is just on the limb of the moon, so it's not clear whether you should consider it near side or far side. So what is the origin of this dichotomy between the near side and the far side? Well, our first interpretation was that one of the big differences between the near side hemisphere of the moon and the far side is that the near side probably has a higher temperature in its interior. And this is because here, this is the Procolarum creep terrain. This is where all the lava flows on the moon erupted. And as I'll show in a second, this corresponds to an anomalous, let's show it next. Yeah, so this region here is where we're probably 95% of the moon's lava flows erupted. So in order to form a lava, you have to melt the underlying mantle. So this suggests that the mantle on the near side of the moon was probably hotter than the mantle on the far side. And this is just showing this in another way. Here this is showing a map of the abundance of thorium, which is one of the primary radioactive elements, which keeps the moon warm. And because of the Lunar Prospector mission, we see that there's this one geochemical province here, which more or less corresponds to where the Mare basalt erupted, showing that there's a high abundance of thorium, but also potassium and uranium, which are the 3 primary heat producers. And here's just a thermal evolution model that a student in our research group made, showing that if we in fact place a large concentration of heat-producing elements, corresponding to this component called creep in the lunar literature, that this region of the moon gets hot and slowly cools down over time. Even at the end of our simulations, it shows that the near side of the moon here is hotter than the far side. So this is a geophysical signature which may actually be visible in the present-day seismic data that we have. Okay, so we ran, using this hypothesis that the near side of the moon is hotter than the far side, we ran some simulations of how this may affect the impact cratering process, and this again was some work done by Katerina Milkovic, who was also in our research group at IPGP. And on the top here is just showing some impact simulations for an impact on the near side of the moon, where the crust is a little bit thinner and a bit hotter, and here's another simulation on the far side where the crust is a little bit thicker but substantially cooler. And besides the difference in temperature, the only real difference between these two simulations, the impact events conditions are exactly the same. So it's the same size bolide impacting into the surface at the same speed. And the only difference between these simulations really is just the temperature of the underlying crust. And what this shows is that at the end of our simulations, because of this difference in temperature, the impact basins on the near side of the moon appear to be roughly 2 times larger than those on the far side, even though they formed with nearly the exact same conditions. So here's just showing the region of crustal thinning on the far side, which is only about 100 kilometers, but when you go look here on the far side, it's about 200 kilometers. So this just suggests that craters on the near side of the moon could be artificially increased in size just because of their hotter temperatures. Okay, so the next thing we did is we took the distribution of the near-side impact basins and we tried to correct the size of these basins as if they formed on the far side with the same temperature, and this is what we get here. And then if you compare the distribution and size of impact basins on the near side to those on the far side, you can see that these two maps look pretty similar. So this suggests that there is no difference in the impact cratering rate between the near side of the moon and the far side, and that the difference in size of the craters that we see, which is substantial, is only a reflection of the surface, the differences in temperature of the surface and subsurface. Okay, so last thing I'll talk about in detail is the question of whether the mantle of the moon is exposed. And I think this is an extremely important question because, as I mentioned before, almost all of the data that we have, especially in terms of geochemistry, comes from the surface of the moon. Yet, at least for the moon is composed of 95% mantle. So if you want to understand the bulk composition of the moon, then you need to understand what the mantle looks like. Okay, so here is just showing the topography or the crustal thickness map. I mentioned before that there's two impact basins in particular, Crisium and Moscoviennes, where we predict the crust to be nearly absent, and we suggested that these basins here may have excavated all the way through the crust and into the underlying mantle. And here, what I'm showing in comparison is the distribution of places on the moon where spectral reflectance data has suggested that there are deposits of nearly pure olivine. So so each one of these squares here, or stars here, is consistent with being a dunite on the lunar surface. And the first thing you should point out is that you should realize that the biggest abundance of these dunite exposures correspond to a ring around the Crisium impact basin here, and also corresponds to this cluster of points around the Moscoviennes basin. And the interpretation of this research group, which is consistent with the GRAIL crustal thickness maps, is that these dunite exposures here represent mantle of the moon on the surface. So we did some impact simulations to see if it's plausible to excavate mantle and to find out where it would actually land on the surface. This again were some impact simulations done by Katarina Milkiewicz. And here, this is just showing a simulation for a 60-kilometer impactor smashing into the moon at 17 kilometers per second, forming an impact basin that's roughly the size of Moscoviennes. And this is color-coded, so the light gray is the crust and the dark gray is mantle. And what you see is you excavate the entire crust here, the mantle rebounds, and as the mantle kind of collapses, you get this thin layer of material which flows across the surface. And we have mantle materials exposed in the center of the basin, but also just exterior to the basin in this region here. And then if we compare this with where we find the exposures of dunite on the surface, we see that there's a pretty good correspondence. First I should mention is that the central portion of this basin, even though it should be pure mantle materials, unfortunately it's been covered over by lava flows, so we can't see the immediate central portion of this basin. But these little yellow stars here correspond to the exposures of mantle, or exposures of dunite, as measured by the Japanese Kaguya spacecraft, showing that they correspond very well with where our model predicts mantle to be exposed on the surface. In particular, just in the interior portion of this basin, just exterior to the lava flows, and then also just exterior to the central portion of the peak ring in this region here. We did the same simulations for Crisium, which is a big basin on the near side of the moon, which formed in a hotter crust, and we find a similar thing here. We excavate the entire crust in the central portion of the basin. Unfortunately, this was later covered over by lava flows, so we can't sound the composition beneath this. But there is a little bit of mantle which is exposed at the edge of the Mare basalts here, which corresponds very closely with where our models predict there to be mantle on the surface. So we would say that most likely these detections of dunite that the Japanese found in their remote sensing data most likely represent mantle. And if you want to understand the composition of the moon, then you really want to understand the composition of the mantle, given that it makes up 95% of the mass of the moon, and that's, I think, would be an ideal place to go for a sample return mission. And this is just showing that there are actually two impact craters which excavated through the Mare basalt in this region, which may have excavated mantle as well. And we're in the process of looking at the remote sensing data to see if, in fact, these craters here excavated mantle. Okay, so that's the end of my talk, and I will leave you with just a animation of So most people don't realize there were two instruments on GRAIL. One was obviously the transponder for measuring the distance between the two spacecraft, but the second was an instrument that was run by students, which was just to take pictures of the moon with a small little camera. So this is just showing a video as we fly over the Oriental impact basin. So thank you very much.